All right, everybody, let's get started. This is the SAAG Security Area Advisory Group at IETF104. If you're not here for that, you can either stay and learn about it or go outside. As Roma said, we got the blue sheets going around, and we've got a JavaScribe and a mint taker already, so thank you for both of those. That's what, Yoav and Jim, right?
Stephen Benhart.
And Stephen, okay, sorry. I was distracted before, so I'm just checking. And we got a couple more people wandering in. All right, so we've got the obligatory note well. And I know sometimes we sort of breeze through this, but main point of the note well is the IPR policy, but also we remind ourselves to be professional and courteous to each other, keep it focused on the technical aspects. And this is what our agenda is looking like for today. We're going to do the usual working group reports, and we've got a couple of talks before the open mic. And thank you to all the working group chairs who sent their summaries in ahead of time. Oh gosh, I'm way ahead of myself. So I'm Ben Kaduk, and this is our new security AD, Rowan.
Howdy.
All right, sorry about that. So here we are with the working group summaries. So we got stuff ACE, Acme, Curdle did not meet. So I guess the I2NSF summary had a question about Yang modules and IANA registries, which perhaps I have heard that rumors that there might be someone who is excited about, but perhaps they're not. Oh.
Yeah, so the issue is that we have a draft for configuring IPsec, and the way they made the Yang model is by just copying the entire IANA registry, including some some shit. Some algorithms that are considered deprecated, like special export grade 40-bit DES. And so the thing is not how to tell them not to put that stuff, but the IANA registry is dynamic. We're having any document might add a new algorithm to IANA, and then what we're going to supposed to in I2NSF make a new version of our document and make obsolete our RFC every time somebody changes the IANA registry. So we're looking for a way to make this more structured so that we don't have to rev our own RFC, just follow the IANA somewhere, some way.
Yeah, so I don't actually recall, is that particular Yang model managed by IANA, or is it separate?
The Yang model is just in the RFC, or will be in the RFC, right? Now it is in the draft.
Sure. I mean, I think there should be a way to have IANA manage the module so that they can, take the needed updates as new registrations come in.
So if there's a way to do it, we'd like to.
No, the problem, Michael Richardson, the problem is that you wind up with an enumerate in the Yang model that lists all the items. And so unless we have changes to Yang that says, here's the IANA registry XML, that's the appropriate list of things, then IANA can't really manage that module without creating a new RFC from it. Because there's an enumeration in the Yang module that lists the choice.
Now, of course, we could get rid of the enumeration and just leave the number there and tell them, go to the number in the IANA registry. And so if a new number is there, then it's just a uint and we're fine with it. But that's not what we'd like to do, but if we have to, we'll do it.
Paul Hoffman, I was just going to say that's exactly what you should do. This comes up every 5 or 10 years for every kind of thing that we do. Yeah, at least in the security area. So I work for ICANN. I definitely don't work for the IANA part of ICANN. If there is something that IANA needs to do for this, it's probably going to be generic, and it's perfectly reasonable to ask the IANA staff how to do this. And even if it's like, oh, they're going to have to do this new procedure, IANA is here to serve the IETF in many ways. That's doable. But I think the actual answer is simply say, this needs to be alive. We're not going to keep it alive. We're going to point over there and maybe give an example, but stop there. But if there is something that IANA is supposed to do generically for this, it is reasonable for the IETF to ask IANA, and that can be discussed.
I hear that there are IANA staff at a booth that you could go and talk to.
So I'm going to suggest that this discussion be, this is Elliot. I'm going to suggest that this discussion be directed to the Yang chairs for an expert view of this. There is a language issue here. Michael's right. There's a language issue here. It just can't be done purely through an IANA action unless you use unless you get rid of the enumerated type field. So I would talk to somebody like Kent, for instance, or one of the other Yang people to just sort this.
I think that was the bottom line from the working group, if I'm remembering right, Yov and Linda.
All right, IPSecMe, Kitten did not meet. Clamps, Mile, MLS, OAuth. OAuth, did you send something in the past 10 minutes?
Yes. Yeah, at 149, we got it.
All right. We were not updating the slides at 149 and re-uploading them. And apparently the data tracker likes to cache the non-existence of them. RATS met for the first time as a working group.
No, after this. We'll meet.
We'll meet. Sorry.
Right after this.
The report is there, you know.
Dave Waltermeyer. Wow, that's loud. You flashed IPSecMe. We did meet today, and we sent the report in.
Yes. Yeah, we got it.
Okay.
It's linked.
We're trying something different this time.
SACM sent something. Sec dispatch. I think we spawned a thread. Oh, you're coming up?
Waiting.
You're waiting. Okay.
I know the alphabet.
So we should randomize next time. We did have a little bit of discussion on the sec dispatch report, which we can keep going. Segment, suit, teep, TLS, token binding, trans.
Yeah, we did not meet. We only have, sorry, this is Paul Artus. We only have a few last editorial things that are happening. We just sent a message to the trans list yesterday. And other than that, we think we are going to be ready for the RFC.
All right, thank you.
And close down.
Declare victory and close down, yes. We got some other related working groups. We did get mail from several of these, which is good.
Is there any other working group that we haven't talked about that someone wants to come up to the mic to mention related work?
Everybody behind me is going to shoot me, but Doe should probably be on that list.
True story. That's a mistake. We'll fix it.
I really should send you an update, but the NTP working group, NTS is done, and we also have two other security related drafts, one on rough time and one on a concept called Chronos. So there is a fair amount of security work related to time going on in the NTP working group, and I didn't send a note, so.
Thank you for coming up now.
This was a working group, but we had there's a side meeting that's sort of been continuing at various ways. I think, Ben, you were there for it. There was an IoT onboarding meeting. There are security aspects of IoT onboarding, I think, that are actually pretty important. And we're going to actually have an interim discussion the week of the 15th of April, I think it is scheduled. I'll check my calendar. But if you're not on the IoT onboarding list and you'd like to participate, feel free to join. And I will remind people again coming up to that interim discussion.
Wes Herdeker, ISI. The other one to note is the KSK rolling long-term discussion being held in conjunction with ICANN, is going on at the moment. There was a BOF this morning about it, where BOF is really a side meeting more like, but a security review of that area would certainly be good.
Yeah, thanks. So we do have a BOF that will meet. I forget which session it's in.
Morning.
I have it written down tomorrow.
No.
All right. So
Yeah, Cacao will meet at Friday morning. And this is about collaborative and automated course of actions. And we're looking at how organizations can share runbook information for their security response teams. And we can talk about that tomorrow morning.
Yep, please come and provide your opinion on whether that's work we should be doing.
two hands on the trigger wheel. All right. So the surprise, the secret you've been all waiting for. Roman and I had to rebalance the working groups between us, and I will be keeping most of the working groups as responsible AD, and Roman has his list there as well. So we look forward to seeing you in the coming meetings. And now we can move on to our talks. So Toma, you're coming up.
Hello. Okay, I'm going to talk about misbinding attacks in device pairing protocols. And the background to this presentation is that in the SEC dispatch in Bangkok, we describe ideas for a new protocol, and Eric Rescorla asked a question about misbinding. And my first thought was, well, how is that relevant? Because this is a pairing protocol. But the nice thing about working at the university is that then we could go off for a couple of months and investigate. And that's what I'm going to present here. So I'll start by explaining what is misbinding for everyone's benefit, or my view of it, and then we'll come to the new stuff about device pairing and device bootstrapping. So what is misbinding? It's basically any situation where you have a node A that thinks it is authenticating to another node E, but in fact it is authenticating to someone else, here B. And why is this happening? Because the node E is being dishonest and tricking A to authenticate to the wrong endpoint. This kind of attacks have been known in the key exchange protocols at least since 1992 with the station-to-station paper by Diffie and others. And these attacks have largely motivated the design of the Sigma protocol family, which includes IK 1 and 2. The attacks have been called variably unknown key share, misbinding, and cuckoo attacks, and maybe something else. So, okay, some part clipped off. Okay. Here is two versions of the attack against Diffie-Hellman, against Poorly Designed Diffie-Hellman Protocol. So in the first picture, A wants to talk to E, but E is evil, and E tricks A to actually talk to B, but A never knows about that. And in the second picture, the same kind of attack where the victim who is misled about the initiator is the responder, is the victim who is misled. And so B thinks E is connecting to it, but it's in fact A who is connecting. And the solution to these attacks is well known. It is being more explicit in the protocol about the identifiers. So you could bind the identifiers to the signatures as in an ISO protocol, or to the session key like in the Sigma protocol. The Sigma solution is slightly nicer, but I won't go to the differences here. Just to show that what this means is that at some point in the protocol execution, the misbinding or attempted misbinding would be detected because some of the protocol fields have wrong identifiers that the responder doesn't agree with. So how serious are these misbinding attacks? Well, it's a little bit difficult to understand these because it's not a failure of confidentiality. You see, the victim actually wants to talk with the corrupt node, so any secrets that the victim will send over this secure connection would go to the attacker anyway. But it is a bit related to, problem is related to authentication. It can lead to failures of data authentication, or we can just call it entity authentication failure. The attack scenarios in the literature, to me, seem a little bit artificial. So one example from Hugo Kravchuk is this, that A is a commander and E and B are fighter jets, and the commander suspects that the fighter jet E has been corrupted by the enemy, and therefore sends a command to E to self-destruct. But because of the misbinding attack, this command actually goes to B. So the wrong fighter jet self-destructs. So this is not really something I can easily relate to my experience of everyday use of IoT devices, for example. But then, as a person who has done some formal verification of protocols and modeling, I think it is, well, misbinding is a violation of a well-defined security property. So some kind of correspondence property. So in the previous cases, it should be the case that if A and B share a session key K, then A should think that it shares the key with B, and B should think that it shares the key with A. And if this is not the case, we have misbinding. It's also it has been relatively easy to solve this problem by binding endpoint identifiers to the authentication or to the key. However, that requires that there must be endpoint identifiers. We must have credentials for authenticating those endpoint identifiers. And on top of that, one endpoint must know what identifier it expects or accepts from the other endpoint. And that is not the case in typical device pairing. So let's see how the device pairing. So I'll first just quickly run through the Bluetooth authentication so that you familiarize yourself with the pictures. So here, the user has two devices, A and B, makes B discoverable on device A, searches for discoverable devices, selects B, then key exchange takes place in the background, and the two devices, as part of that key exchange, show two 6-digit codes to the user. This is the out-of-band communication, and the user, if they are equal, accepts those 6-digit codes. And right, now the devices are paired. This is what happens when things go well in Bluetooth pairing. So then let's see the misbinding case. So in misbinding, as always, one of those devices has been corrupted. So in this case, it could be just a malicious app on the mobile phone that can control the screen and spoof the pairing user interface. So not any more corrupted than that. And in the next room, we have the attacker with the second phone. And in Bluetooth, they can just name that phone B, or if they couldn't, then they could modify the messages on the air to pretend that it's B. And now the user chooses B, but the wrong B, and the key exchange happens between the two wrong devices. And the two devices show the 6-digit code. And how is the user now going to access? Is the user going to accept this? Well, the attacker can relay the 6-digit code to the compromised UI and show it to the user. And user thinks everything is okay, accepts this, and we have the wrong devices paired. So as you see, this is not really an attack against Bluetooth. It would work for any kind of out-of-band channel authentication in device pairing. It's an attack against the user interface level and not against the protocol details. But let's still look at the Bluetooth protocol. So why doesn't Bluetooth detect the misbinding, and could it detect? Well, the devices here have no verifiable identifiers at all. There is the Bluetooth device name, which the user can set or which can be edited over the air. Also, there's channel binding to the Bluetooth or MAC addresses of the devices, but one device doesn't know what the MAC address of the other should be. So the authentication is really based only on the user's physical access to the two devices, and that's why we can't bind to that identity of physical access. So then we were wondering, Bluetooth has been analyzed so many times by researchers and others, and there are formal models of Bluetooth. So why was this attack not caught? There are so many suggested attacks that we could find in the literature, of kind of marginal weaknesses in Bluetooth or things that could go wrong, but not this exact one. At least we couldn't find it. So we modeled Bluetooth in the ProVerif formal modeling and verification tool. And the trick there to get this attack, which we already knew about, was to use the physical channel that the user uses for communicating with the device as the device identity. And then we could express a correspondent property between the user's intention to pair two devices here, A1 and B1, and then the completed pairing, which is between some different pair of devices. Okay, so it's easy to model protocols when you know the attack that you're looking for, but interestingly, this formal modeling yielded another attack, which we call double misbinding, and there's a picture of it. So in this case, in the other room, there is no attacker, but there is another user with two devices of her own. And each user wants to pair at the same time their own two devices, but one of each user's devices is corrupt. And these two corrupt devices can collude and trick the user to actually pair the two good devices between the users, which was definitely not their intention. So what did we learn here? Well, I think the main lesson is that all device pairing protocols are vulnerable to misbinding if the devices have no verifiable identifiers and if authentication is based only on physical access. Another view, though, to this is to think about it as a trusted path issue. So if the user cannot know that it's talking really to the pairing part of that protocol, but it may be talking to a spoofed user interface, then software attacks can work here. And of course, the user should also know that it's talking to an authentic device and not an attacker's substituted or modified hardware. So that's about device pairing. Then, as I told in the beginning, we were looking at the bootstrapping protocol that connects an IoT device to the cloud. And the example I'm going to use here is EAP-Noob, our own protocol, but we don't go to the details of the protocol. So the only thing you have to need to know that it's an EAP method where user-assisted out-of-band authentication is used for connecting a new smart device to the authentication server somewhere in the cloud. And here is the architecture. The communication goes mostly over the EAP tunnel in-band through the AAA architecture, but then the authentication happens over the user-assisted out-of-band channel. And there's details to the protocol, but we don't go into those because the attack is really on the user interface level. So here is the misbinding case for EAP-Noob. Here the new smart device has been compromised. So as in all misbinding attacks, one of the endpoints that the user trusts wants to connect together has been compromised. And again, it has been compromised only on the user interface level. So the input or output of this out-of-band communication is in the attacker's control. And in the next room, there is the attacker with another device, which it's hoping to connect to the cloud server, but it has no account there and shouldn't be able to do that. That device can also connect through the AAA architecture and with EAP to the cloud server and initiate this pairing. Well, now the attacker would like the user to pass his out-of-band message to the server to register that wrong device. How is that going to happen? Well, the attacker relays the out-of-band message to the compromised user interface, which gives it to the user, and then the user delivers the wrong out-of-band message to the cloud. And as a result, the wrong device gets registered to the cloud server and associated with that user's account. So why is EAP-Noob vulnerable to this attack? Again, it's a question of user physically identifying the peer device and that there's no other authentication. So it's not the flaw in the subtle details of the protocol designs a missing field. It is an inherent weakness in peering protocols that rely on the physical access for authentication. This same kind of weakness would appear in any other device bootstrapping protocol, registration protocol. For example, DPP, when Wi-Fi gets it, it will be vulnerable to the same attack. The only place actually where we found that such similar attacks have been investigated in research literature on this device registration is related to trusted computing. There they are called the cuckoo attacks. So if you have a trusted execution environment in a device, you can create a secure connection to it, authenticate it. It may attest to the integrity of the software on the other software on the same device. And all looks good, but you have really no way of knowing that the secure connection is to the heart of the same device that you are touching with your hands. And this problem may be relevant to two working groups at IETF, RATS and TEEP. RATS, I believe, is meeting still today. Okay, I have two more slides, just a summary of what we can do to mitigate the attacks and then the final summary. So I don't think there is any way of avoiding these attacks completely, but there's some things that we can do to make the attacker's life more difficult. So one thing is to bind the session keys to any context data that we may have available. So for example, channel binding to wireless MAC addresses may force the attacker to active attacks over the air interface. And if the devices have persistent non-modifiable identifiers, or if they communicate their hardware information in the protocol, then it makes it more difficult for the attacker to replace the device or provide a fake device to the user. Then, as mentioned, trusted path could help here if the user knows that this is an authentic device by a specific vendor, unmodified, and the user has a way, such as pressing a reset button, of communicating to the real registration or peering process in that protocol, then that might solve the problem. I think the main defense that we have is asset tracking, that is knowing which devices you have, how many of them you have, what the makes and models and serial numbers are. And then in that case, device certificates can help to bind the device identity to the registration or peering protocol. Okay, so to summarize, I believe now, after this investigation, that all device pairing and bootstrapping protocols are vulnerable to misbinding if the device authentication is based purely on physical access, and if device identity either is not cryptographically authenticated, or even if it is cryptographically authenticated, but the other endpoint doesn't know what is the correct identifier. And as said, we have ways of mitigating the attacks, but no complete solution. And my question or point for discussion for the audience is whether we should now think that Bluetooth and other device pairing protocols are inherently insecure, and the same for TE provisioning and smart device bootstrapping. Thank you.
Oh, thank you for the talk. Do we have any questions or your comments about this discussion question?
Hi, Jim Fenton. I'm wondering if you've also looked at any of the out-of-band authentication protocols that are in use. I mean, not nearly, not a situation where you necessarily have physical proximity as much, but we also have the issue frequently with trying to securely bind a transaction happening on an out-of-band channel to some sort of session being authenticated, where you're trying to prove, say, that you've got your phone and you're approving a transaction here. Have you looked at that use case at all, and does the same work? It seems relevant somehow.
I think it's a good point. We haven't considered that if you're thinking like using mobile phone to confirm a bank transaction.
Yes.
That it is a little bit different, because there you usually have a two-way authentication for the in-band channel first with the existing pre-established credentials. Whereas here we have no pre-established credentials. So there might be some similar aspect of misbinding if we assume that the pre-established credentials have been compromised. But I'm not sure if that is. I think it's a little bit far to go.
If the pre-established credentials are just something like a password, I mean, it's the weakness of that that is the reason that we're doing this in the first place. So
might be.
Daniel Kahn-Gilmore, ACLU. Thank you for this work. I think we really need, it's really nice to see somebody doing this kind of abstracted thinking, which we need more of in terms of thinking about how these protocols fit together. I apologize that I have not read the details of what you've written, but my concern is, excellent, thank you, much appreciated. I'll try to memorize that number before I sit down.
The slides are in the data tracker.
Thank you. The way you say physical access, at least in this presentation today, is open to some potentially vague interpretations. And I wonder if we said like these two Bluetooth devices were in a Faraday bag together, if that would satisfy your concerns. I'm not suggesting that that's how we tell everyone to pair their Bluetooth devices. I'm just wondering if you have a sense of what the boundary is for physical access.
It's true. That's actually something that has been suggested in a related case in the literature about putting two devices, like pairing ad hoc network devices, for example, putting them in a can and shaking them together or something. That that might, it's true that you might be, you're better off if you are in a Faraday cage with only your devices and you check that there's no third device in that room, and then the misbinding can't happen. If you only have two devices that they are able to communicate with each other.
Just to clarify, Stefan Santosson, AAA Security. Just a clarifying question. Did your attack require the user's device to be compromised?
Yes, that's the whole point of. I mean, that's the nature of misbinding attacks.
Yes.
So the type of attacks that we were investigating are ones where one of the user's two devices is compromised, or one of the two endpoints that the user wants to connect to each other and authenticate to each other. One of them is compromised, and that compromised device plays the tricks and causes the connection to go to another device, the third one.
Okay. Then in that case, I think it's a very interesting talk, but I don't think that shows that the protocol is inherently insecure.
Well, that's a positive worldview.
And Max Pala, Cable Labs. Thanks for the work. I really appreciate that. As DKJ said, abstract thinking and thinking about out-of-band channels is something that we should start doing. One of consideration and goes into what you just said before when you replied. It seems to me there's a problem with we're trying to authenticate one channel and we rely on another channel which we don't require any authentication at all. So the out-of-band channel usually is the security of that is very ignored. Think about using SMS or something similar. And this is the source of the misbinding practically, because you cannot authenticate that that's the right source.
Yeah, well, it comes to how you define. It can be that is one way of viewing it.
I just want to put it in another
yes,
option.
it definitely is one way of viewing it.
If you view in this way, that might be something that may be easier to work on if you say out-of-band channel needs some form of authentication.
But
it may be difficult, but
I think that then we are kind of giving up on physical access to devices as a way of selecting the endpoints.
Just some parameters needs to be added to that. Physical access, it might be a little bit too permissive if you want to try to avoid this. If you're okay with this because you say, well, I'm activating my device, I'm home, there's nobody really around, I'm fairly okay with it, that's one argument. But in other environments, like where you have many devices at every time, work environments, wide area networks, etc., that might be
I think this is a general problem with the bootstrapping, that there's so many proposals that just have no security at the bootstrapping stage.
All right, so we're actually a little bit over the time we allocated for this slot, so let's cut the mic line here, but drain the queue.
Okay, I'm Anu from CDAC, India. So you are saying that an attacker can send a OOB message to the device, and then that OOB message will be communicated to your cloud server. And so misbinding will happen in that way.
Well, misbinding really, not the attacker sending the device, but the attacker in this example spoofing the user interface of one of the device. The device that outputs the out-of-band message, or in some other protocols inputs it.
No, so in that case, even if you use device certificate, that also can be changed.
Yes, the device certificate doesn't help unless the other device knows what name and certificate it wants to see.
Then why are you suggesting that device certificate you help in misbinding?
Well, if you do this tracking of connections between, like if your devices report to, let's say, a central server, and where you can see, or on the device you have a user interface where you can see what everyone is paired with, then you would see that there is some redundant pairing with the device that's not, you didn't think you have.
No, but then it means that your device is already connected to the pairing server. It means that you do not require this bootstrapping at all.
The attacker's device, so the attacker's device in the other room would not be one of your devices. So you would kind of see that you have an extra device, one that failed to pair, and then another one, then another endpoint that seems to be paired. So if you have this global view of things, tracking your devices and their connections, their names, then there's many places here where you might catch that something is wrong.
Not really. Anyway, once you are connecting your device to the cloud server, and you can see that OOP message, even if you transmitted the OOP message, but the device could not connect, and a man is present to send that OOP message. So anyway, they will know that this is a misbinding because my device could not connect.
That is one of the solutions which we have for EAP noob proposed, definitely, but that is kind of okay. So it then we depend on the user checking on checking that both devices. If the user checks that both of his devices are connected, then they notice that one of them is not connected.
So, I mean, if the attacker can relay the original out-of-band message, they can continue relaying some stuff and showing a spoofed UI for a while.
Yeah, so attacker can of course relay, but then the point of this misbinding should be that, I mean, otherwise you can just do relay attacks, and the point of misbinding should be that eventually the attacker doesn't, maybe this compromised device is thrown away and into the shredder. But I understand I think you make valid points.
And most importantly, sir,
we shouldn't go through all these possible defense mechanisms here.
And most importantly, since manual intervention is there, so a person can himself create a key pair to start the communication. It doesn't need to go through all these OOP messages.
There's many ways of designing device pairing and bootstrapping protocols, and in some cases maybe I'm not sure, but
yeah, I mean,
I'm not proposing a solution here or arguing for one specific solution.
Yeah, let's keep this discussion going on the mailing list. I think we should move to the next question.
Yeah, Daniel Franca Akamai. So thank you for this talk, because I have a new up-to-date case study as to why really simple, lightweight tools like Proverif and Tamarind still matter. I get a lot of incredulity sometimes that these things actually find anything that isn't already obvious. And well, if you're steeped in this stuff long enough, it eventually becomes obvious. But 25 years after Needham Schroeder, we're still writing exactly the same bug.
Okay, thank you for the question. I really want to answer this, because my view of these verifiers has long been that they don't find any new attacks. It's the smart person using them who finds them. But they do work as debugging tools for obvious mistakes. But in this case, I think it's the first time I actually found a new kind of attack, the double misbinding, using one of those tools. And every protocol I have designed, I've tried to model.
All right. Well, thank you, Tomas, for the talk. And John, you're up next.
So I'm John Mattsson Eriksson. I plan to tell you what 3GPP is up to when it comes to 5G encryption, and see if anybody in the IETF has similar problems, thoughts, ideas when it comes to high performance encryption. And 5G will do many things, but one of the things it will do is to vastly increase the amount of data that you can send over cellular networks. But first, going back a little bit of history. So these are all the current algorithms that has been used or are used by 3GPP cellular today. You might not know all of them, but probably all of you have used these algorithms every single day, and will probably continue to do so. So for 4G and 5G, early releases of 5G, 3GPP relies on AS, encounter and CMAC mode, and also on SNO 3G. SNO 3G was standardized for 3G, also used in 4G, 5G, and has been backported to 2G. And after AS, DES, RC4, maybe ChaCha is probably one of the most deployed, used, and analyzed ciphers in the world. So these are the algorithms, 128-bit algorithms used in the first releases of 5G. 3GPP is planning to look at 256-bit algorithms for later releases. And there are several reasons for this. One is the quite high requirements on speed. ITU has made requirements for what you need to have to call a standard 5G, and that is a minimum of 20 gigabits per second downlink. These might not be reached by early implementation, but later releases of 5G will probably significantly surpass this. This was what was done with 4G. Another requirement is network function virtualization. 5G will mainly be deployed as software-defined virtual networks with various degrees of specialized hardware. Hard to say at this point exactly what. So basically all the current algorithms are too slow to do 20 gigabits per second in software with good performance. AS-CMAC has similar performance as AS-CBC mode. You cannot reach 20 gigabytes. You get around 9 on a single core. AS-256 GCM, on the other hand, has excellent performance. You can reach over 20 on a single core. You could also parallelize it. So this is obviously one of the main candidates for 3GPP going forward. But 3GPP, as you've seen before, likes to have backup algorithms. We don't want to rely on one algorithm. We want to have several algorithms implemented everywhere, so if a weakness is found, we can switch immediately. The backup algorithm chosen by TLS and IPsec, ChaCha20, is simply not fast enough. You can reach 4.5 on a single core. You can parallelize it, but then you're starting to use many, many cores if you want to reach even 20. The other reasons than performance that 3GPP is looking at choosing new algorithms. One is usage by government. There's a lot of governments interested in using 5G, and they have requirements to have 256-bit algorithms everywhere. And the third reason is to make the algorithms future-proof. If you design new algorithms today, there's no reason to not go with 256-bit keys. As a related activity, the CSER AAD competition recently published its final portfolio, and it has 2 candidates for high-performance encryption, AS-OCB3 and AEGIS 128. The second algorithm here is only specified for 128-bit keys. At least that's the only one included in the final portfolio. It will probably not be the choice for 3GPP. So what are the other options? Snow was designed by the cryptographic team at Lund University. Lund is a town in southern Sweden. And they have now updated the previous version of Snow and made a new version called Snow-V. And this team is led by Professor Thomas Johansson. I'm not going very much in detail of how this cipher look at. All the Snow ciphers looks very much the same. They have a linear part with 1 or 2 linear feedback shift registers. They have a non-linear part called a finite state machine. And the design criteria, the revelation when trying to see how fast they could get Snow 3G to run on in software on modern hardware, they realized that by updating the cipher slightly, they could make it run significantly faster. So the design criteria for Snow-V is to build on the old versions and all the analysis done for that, and design it to be as fast as possible on modern CPUs. And the main things to make this happen is to use the AVX2 registers, SIMD, and then it also uses the AS round function in the nonlinear part. It also expands the state here in the final state machine. And this design goal of this security goal is to be as secure as AS256. This is the last slide. So what have the team in Lund University achieved? They have achieved quite outstanding performance in software on a mainstream laptop, single thread, single core. Snow-V performs 60 gigabytes per second. Note that this is only encryption. It does not include integrity. Adding integrity would slow this down slightly. I don't have any exact numbers. Snow-V also performs extraordinarily well in hardware. Straightforward implementation reached 700 gigabits per second, and they expect it to reach over 1,000 in a 7mm process. Next steps, more security analysis. This has been designed with the knowledge of the Snow cipher, and they have, of course, evaluated the new design with all known attacks, but more security analysis, especially from independent cryptanalysis, would be needed. More performance measurements, for example, on ARM processors. Amazon recently released ARM processors in their cloud, and they have very good price performance characteristics. So I would not be surprised if ARM processors are used very much more in the future. We don't have any measurements for that yet. Then the authors tell me that currently GCM is the performance bottleneck here. The paper published uses GCM for integrity. So they say that they will evaluate if there's any faster options. For example, Poly 1305 or anything else published lately. The process in 3GPP is that 3GPP has given requirements to ETSI-SAGE. ETSI-SAGE is like CFRG for 3GPP. ETSI-SAGE will then recommend algorithms to SA3 after probably a lot of ping pong with license. And then the final decision lies in 3GPP SA3 to decide what is used. Conclusions here is that we see that by designing new ciphers for modern CPUs, you can reach extremely good performance. And I would like to know if anybody else have any thoughts about high performance encryption in virtualized environments, and especially what I think ASGCM is probably a default choice, but what should you use as a backup?
Max, you coming up?
Max Pala Cable Labs. We actually have the same problem. So we have, the new standard for 10 gig. So we're trying to find out how can we handle this large volume of traffic that will really come soon. We already started deploying 1-2 gigs links, and our CMTSs handles, a large number of these. So we're definitely looking into similar approaches. Our environment might be slightly different in the requirements that we have, in the sense that being wired and not wireless, we might choose slightly different paths to reduce the security for the link, depending on for how long we want that data to be secure. So since this is network traffic that we're protecting, and we expect users to actually protect their communication with TLS, etc., at a higher level. For our use case, this might suffice. But we were just talking with some people at NIST. We might look into that for general access networks. So that might be something that we can collaborate on.
Yeah, would be great.
Kenny Patterson, thank you very much for this nice and informative presentation. I'm sorry we didn't have time for it at CFRG earlier in the week. I just wanted to make a point that you compared Etsy Sage to CFRG. They're somewhat different. So Etsy Sage in particular actually has financial resources to commission independent cryptanalysis. And I was actually leads to a question. Do you think they'll do that in this case for 5G?
I would guess that the answer is yes.
Okay.
I don't know at which stage, but probably yes, unless they choose like ASGCM, which has been analyzed. Yeah.
Thank you.
Hi, this is Sean Turner. Excuse me. You alluded to the, I guess, IPR licensing rules. And so I hope that one of the main things that they pick is that if they pick one and then this later comes over to the IETF, that they have reasonable licensing terms. I would hate for them to pick something that's crazy that ends up causing lots of problems over here for us being unable to adopt it for whatever reason. Yeah.
As far as I know, there's no IPR on this cipher. I don't know what other ciphers Etsy Sage is discussing.
That's fantastic. Thanks.
Hi, I'm Yavnir from Dell EMC, and that's kind of relevant because earlier this month I tested with one of our servers, and I used stock OpenSSL to measure speed, and I got about 38 gigabits per second for ASGCM. So that's kind of a higher number than what you've shown.
Yeah,
and
I think these are a couple of year old processors. So it makes sure I think they have double the amount.
And what was surprising for me was that for Chacha 20 Poly 1305, we got about half the speed. So not quite 20, but 18.
Okay, that's interesting. Yeah. That's news to me. Thanks.
All right. Thanks, John. That was a good talk to have. I'm glad we could find you a home since CFRG had such a packed schedule.
Just open mic. We'll do open mic in there. So based on the agenda, we have open mic time. So if you want to bring anything to the community, please come on up. Hey, Max.
Hey, Max Pala, Cable Labs. I recently started a discussion on the mailing list around some encoding, but some things that we are working on in LAMPs especially, or we're trying to propose in LAMPs, is the use of multiple public keys and multiple signatures in certificates to actually allow us to deploy hybrid PKIs that might use different algorithms. This can be used for post-quantum resistance today, or could be just combining two different algorithms for compatibility. In general, the approach here is that you can combine different algorithms as you like, basically. This can be used for algorithm agility or what we call deferred algorithm agility in the future. one of the things that came up in the discussions is the fact that these certificates, and this is a tendency that we see from CFRG for all the algorithms that we're trying to come up with for the next generation. We see an increase in key sizes and signatures. This, besides the idea of combining with traditional crypto, is a problem that I would like to bring up to this in the security area and start with maybe looking into what is the impact over many other protocols, right? The most noticeable one is TLS, that historically might have problems with big certificates. And another point that I would try to bring out is that it's not just certificates that will be increased. It's going to be CRLs, it's going to be OCSP responses, everything. The tendency in cryptography is to have bigger, the need for bigger authentication data than smaller. And I don't know if we should bring out the discussion about trying to design systems that will take this in consideration, maybe not today, but in the near future, because I saw that the tendency is, well, certificates now are small, we can make it smaller and smaller and smaller. But this is a gift that we got from ECDSA, and I don't think this is going to repeat itself in the future. And I really need to plan. Now, my job is to plan today, to think in 10 years for deployment, and to think in PKI terms in 50 years. So I need to start the discussion today. And I don't know, and I would like to know what the personal opinion or opinion of the chairs are in this area, and if they think it's something that we should start thinking and maybe more formally work on that. Thanks.
I mean, I'll let Ben speak as well. I mean, in my opinion, certainly that's something we should be working on. I think to make kind of tangible progress and to be able to figure out how to work on it, we need to set up what are the constraints. So what is the box we're trying to kind of fit in? And then once we have those engineering goals, we can figure out how to move out on it. And, whatever that might be, help with, CRFG, or we do kind of something with the new working group. But I think we got to know the bounds in which we're trying to create an optimization and we're trying to make sure we can fit in.
Yeah, I mean, I don't have a crystal ball, but the trends, I agree with you. The current trends seem to point towards at least the potential for larger signatures and cryptographic objects. And I think you're right. If we do need to be thinking on 10-year time horizons, we got to be planning about what's going to be affected. Are we going to have our cryptographic handshakes? They're just a lot harder to do because they fill up our data pipelines or something like that.
Yeah, that's exactly the point. And I'm just a little worried today that, when I see, protocols that are being developed or discussion happening, is that it's accepted the fact that certificates should be small. And this is definitely, according to my experience, I don't have a crystal ball, absolutely, but in my experience, it probably is going to be a lot bigger. And we're talking about, in some cases, 40Ks, not just few hundred bytes more. And the impact could be very, very, very relevant to this community. So I need to deploy this infrastructure, and I would like to have the internet protocol be able to deal with that. We're doing, in our infrastructure, we don't have this problem because we can handle our protocol, so it's easy. But when we expose this technology to the open internet, we need to be able to say, yeah, this works with TLS, so you can protect yourself with other algorithms, not just the one that we use today. Last consideration, it seems like we have a lot of fragmentation even today with some big RSA keys. So it's not a new problem. So it's something that I think we should try to address it.
Okay, Javnir, there's this idea of doing a Sunday tutorial, either next IETF or the one after that, about writing security considerations, because we all know some people don't do it very well. So I volunteered for that, and Linda Dunbar volunteered to help. And
And we appreciate that. That's wonderful.
Great. So what I plan to do is make a really rough chapter kind of outline and put it on GitHub, then send a message to the SAAG list and more importantly, the SecDir list, to have people look at it, post pull requests and stuff, so we can get an outline ready, and then we can make a presentation out of that. So we'd appreciate anybody's help.
Again, that's wonderful. I mean, we've talked about this on and off, so you taking a concrete step forward is very helpful. Much appreciated. All right, other folks at the line, at the mic. Going once, going twice. So if not, Ben and I wanted to cover a very important agenda item that we would have done kind of up front. So speaking for myself as the incoming AD, I'm stepping into very large shoes, and we prepared kind of a gift for Ecker here to recognize all of his help. Unfortunately, despite not being an AD, he's fixing everyone else's protocols right now, regardless. So when you go out and kind of in the hallway and you see him, please do thank him for all the hard work he did, both inside our security community and how he's made sure that that has leaked out into everything else that the IETF is doing. So please track him down and give him a hearty thank you. So with that, we're concluding SAG. Thanks so much.
Thanks. And who has the blue sheets?
Blue sheets to the front, please.
No, yeah.
I wonder about this, if you focus on the but then people tell you that the 5G is all about these billions of devices and short latency. So you use one core of the processor for your So how about
Sure. Yeah, please, if you would mind.
thousands of devices and use how does that happen? I'm not familiar with algorithms, but I